Hello everyone. This is the introduction to Applied Wave Research AWR, where we are going to draw the 3D planar electromagnetic structures. So we have got different products in AWR, which includes the Microwave Office, Visual System Simulator, Analog Optics, AP-LAC, Axiom, and Analyst. So in our laboratory, we are going to make use of Axiom. The Axiom simulator, it is used to analyze the 3D planar EM structure, and here are some of the capabilities of the Axiom tool, so which can be used to draw the layout, or in the layout we are going to draw the structures, and then we are going to analyze them for the discrete and fast frequency sweeps, as well as for the it provides us with the solution for our S parameters, and then we can also optimize the geometry and create the parameterized models. And here are some of the applications of the Axiom simulator. So this simulator is used to design the on-chip passive components, and we can also make use of this for RF PCB module and packaging interconnect, as well as we can design the antennas and antennas arrays. So this is the list of the different features of Axiom. We have got different features so which are listed out. Here is one with antenna analysis and post processing, where we are going to measure the antenna parameters, which includes gain, as well as we can also design the structure for linear, circular, or for different patterns of polarizations. And we have got the other features too. In our lab, we are going to design the microstripline resonator. The microstripline resonator is as shown here. We have got a strip line, or this is the conducting strip, which is separated from the ground plane with the help of the dielectric layer, or which is also called as substrate. The dielectric substrate that we use here is FR4, which is of low cost, or we can also make use of other substrates like alumina. The structure can be done as shown here. The length of the structure is taken as L, which is the length of the microstrip line, and which is given by the equation lambda g by 2, as well as we have got the feed lines here, which is of length LF, and we have got some spacing between the strip line and the feed line, which is taken here as S. So the spacing here provides the coupling between the feed line and the microstrip line. And here are some of the specifications which is given to design the structure. The specifications are like resonating frequencies given as 2.5 gigahertz, and the substrate parameters are given, where dielectric constant is of epsilon r is 4.3, and which is the thickness of the substrate, which is given as 0.8 mm, and we have got the tan delta value, which is the loss tangent value, which is given as 0.025, and the characteristic impedance Z0 is 50 ohm. The length of the strip is given here as L, and the strip is fed with the help of the feed lines here on the either sides, and the length of the feed line is given as LF. So how we calculate the length of the strip? As well as we can see, there is some spacing between the feed line and the strip line, which is represented here as S. So the coming back to how we calculate the length of the strip is, the length of the strip is calculated with the help of the equation lambda g by 2, where lambda g is going to be the guide wavelength, and it is given by c by root of epsilon e into f. So in order to know what is epsilon e is the effective permittivity, which is given along with the relative permittivity, but we don't know what is the actual width of the strip as well as the thickness of the strip. So in order to calculate the width and thickness of the strip, we have the equation knowing what is the characteristic impedance Z0, which is 50 ohms, and knowing the dielectric constant epsilon r, which is 4.3, we can calculate what is the width of the strip, which is W by D, Since it is a huge equation, we go for the online available microstrip line calculator, and the link is given below here. So once we calculate what is W by D, we substitute for the value of W by D in the effective permittivity equation, and we get to know what is effective permittivity, and then substitute the value of epsilon E here and get to know what is the guided wavelength. And after knowing what is the guided wavelength, we can substitute for the value here and know what is the length of the microstrip line is going to be. So once we know what is the length of the line or the length of the microstrip line, we can also know what is the value of LF feed line, which is given as L by 10. So this is how we calculate for the different values of length, different lambda g, and we will know, or we will draw the structure. So after drawing the structure, we expect the simulation results to be as shown here. The structure here is designed to resonate at 2.5 gigahertz, that we can observe that from the S21 parameter. So this is the transmission parameter of S21, which means from port 1 the power is being transmitted to port 2. So when the power is being transmitted from port 1 to port 2 and at resonating frequency 2.5 gigahertz, we expect the power delivered to port 2 at this frequency is high, or it is maximum, and at rest of the frequencies it is low. And similarly, when we measure what is the reflection parameter, which is S11, that is the power is being reflected back to the or in the same port, which is given as 1 and 1. So we can observe from the graph here it is very less, that the power reflected back to the system is very low. And so we can go ahead with designing such a system for different values of tan D as well as for different spacing of S. Hello everyone. Let us start with the creation of the structures using AWR design environment. To do so, go to the AWR design environment, which is on the screen. Double click on it. The version we are going to use is 9.06, which you are able to see here. And now, first you need to create a new project of your own. For that, go to File, Create New Project. And once the new project is created, we have many other simulators to use. We are going for Axiom simulator for analyzing the structure. So now first go to the EM structures, right click on the EM structures and right click on the EM structures and create new EM structure. The new EM structure window opens where you can name the EM structure, and here I have named it as EM structure 1, and you need to select AWR Axiom and then create. The EM structure drawing window appears on the screen as shown here, and once the screen is done, before doing the structure, define the units for drawing the structure and the frequencies of operation to see the simulation results. To do that, we are going for the project options, which is appearing here under the project, and click on the project options. You'll be getting a project option window. So in project option window, you are now supposed to define the global units. The global units consist of the frequency, angle, temperature, the length of the structure that you are going to draw. See to that the frequency is in gigahertz and the angle is in degrees, and the length should be of the type millimeter. So set the length to millimeter and then go back to the frequencies, and now here you can modify the range of frequencies that you want to see the sweep of the simulation to appear from. So let us take the start frequency is from 1 gigahertz to 3 gigahertz, and let us take the step size as 0.1 gigahertz. And once this is done, you need to always add and then apply the thing. So once the application is done, you are able to see the current range of frequencies which are going to appear from 1 in steps of 0.1 till 3. Then the sweep type, we are going to choose it as linear sweep type, and then you need to click on the OK button. To define the material properties, click on the drop down button of the EM structure. You will be getting enclosures here. So double click on the enclosure and an enclosure window opens where you are going to have the definition of the materials, the dielectric layers that you are going to use, and the type of material you are going to use to do the structure. So now first let us go to the materials where we have got already predefined material properties which is earlierly used. Our duty is to delete the materials which are used earlier, and once the deletion is done, you can add the new materials again. Same way, the dielectric layers which have been used earlier has to be deleted, and even the material definitions has to be removed. Go to the enclosure in the enclosure properties option. Give the grid size of X as 0.1 and give the grid size of Y as 0.1, and then go to the material definitions, and now we need to add the dielectric definition. To add the dielectric definition, click on add button, and you can go to the preset. Here we have got different types of dielectrics which can be used, and we are going for FR4 as a dielectric, and the epsilon r value is given as 4.47, and we can give the thickness of the dielectric, that is tan d, so it is given as 0.016, but we can give it as 0.25 and click on the OK button. The conductor has to be defined. In order to define the conductor, we need to add a new conductor. The conductor we are going to choose is copper. From the presets, choose the copper and click on OK button. Now we need to add the dielectric layers. The air is already predefined and it is default. We need to add the thickness of the air as 20 mm, and then insert a new material definition. So in the new material definition, you need to choose FR4 for the second layer, and you need to give the thickness of the second layer as 0.8 mm, and then see to it that the top boundary is approximate open and the bottom boundary is perfect conductor. So once the dielectric layers are defined or materials are defined, you can go to the material. In materials, you can give the material definition. So to do that, insert the material definition which is named as trace 1, and in perfect conductor we are going to choose the copper as the material, and the thickness of the copper has to be given as 0.01, and then once all the things are defined, the structure can be done and you need to click on the OK button. To draw the structure in the EM structure window, you need to go to the draw option, and in draw you have got predefined shapes which suits for the structures that you are going to choose. And now I am going to choose the rectangle as the shape and bring the cursor to the drawing window. And once you bring the cursor to the drawing window, click on the space bar. You'll be getting with the coordinates where you are going to enter the starting corner of a rectangle, and you are going to enter the starting corners as 0, and even for y value you are going to enter it as 0 and click on OK button. So you are able to see that the starting point is going to start from at the exact center of the thing, and it is at the coordinates x equal to 0 and y equal to 0. Again, to enter the opposite end corner values of the coordinates in a rectangle, click on the space bar, and in space bar now we are going to enter the value of dx and dy. The value of dx you can enter as 33 and the value of dy you can enter it as 1.533 mm and click on the OK button. To bring the structure into visibility, go to the view option and click on view all. So you are able to view the structure which you have done. To this structure, we should add feed lines to the structure. So to add the feed lines to the structure, again go to draw and select the rectangle. Leave a space of 0.3 mm from the structure. Now enter the coordinates to add the feed lines. The coordinate now is going to be minus 0.3 in the x direction and it is going to be 0 for the y coordinate. So once the x and y coordinate are added, click on OK button. And again you need to add the structure width and height, which is going to be dx and dy. And now for dx you need to add it as minus 3.3 in the x direction and now the y is going to be 1.533. So click on the OK button after adding the feed line. Now you are able to see that the feed line is been added with a space of 0.3 mm from the earlier strip line which we have drawn. So the same way you need to add another strip line at the other end of the microstrip that you have drawn. To fix the feed line at the other end, again go to draw option and choose the rectangle. So once you have chosen the rectangle, you need to give a space of 0.3 mm at the right edge of the strip. So to do that, enter the x and y coordinates value. The x value you need to enter it as 33.3 and then the y value you need to enter it as 0 mm and click on the OK button. In the similar way you need to add the dx dy coordinates, and the dx dy coordinates is going to be dx will be 3.3 and dy is going to be 1.533 and click on the OK button. Once the thing is done, to view the whole structure and the feed lines, go to the view option and click on the view all button. So now the structure is ready. To this structure we need to add ports at the edges of the feed lines. So to add the ports at the edges of the feed lines, select on the feed line first and then go to the edge port option, bring the edge port and add the port at the first feed line. And similar way, go to the other edge and bring the edge port and add the port to the another feed line. So now the structure is ready. You need to save the structure. To do so, go to File, save the project, give the title of the project as SV. I am giving it as SV Resonator 1 and you can save the structure. So once the structure is saved, you are able to view the structure name as SV Resonator 1. Now you need to analyze and see the simulated result. To analyze the things, you need to add the graphs. So in the project options, go to the graphs, right click on graph and create the new graph. In new graph, you need to enter the name of the new graph as Resonator and you need to choose the rectangle option and click on OK button. So the graph is done. To this graph we need to add the measurements. So under the graphs, go to the resonator, right click, add measurements, and you need to add the measurement type as port parameters, and the measurements that we are going to do is with respect to the S parameters. and the data source name is to be chosen as EM structure 1, which we have done. And now we need to add the 2 port as 2 and from port as 1, and then see to it that the complex inside the complex modifier, the magnitude and the dB are checked, and then apply. Click on the OK button. So here we are able to see that we have added the measurement, and now we need to see the simulation results. To do the simulation results, we need to go to simulate and click on the analyze button. So it starts simulating. Since the simulation is taking too much of time, it means there is some error in the grid size. So click on the cancel button and again go back to the enclosures, and in enclosures check for the grid size of X and Y. The earlier grid size we have given was 0.1 for Y, and now it has been changed for 0.01, and you need to change it and click on OK button. Again go to simulation, analyze, and see how fast the results are being generated. The result is now ready for analysis. We can also add the marker at the tip of the resonance that we have got, add marker, and now we can see that it is resonating at a frequency of 2.402 gigahertz, and at a attenuation is occurring at -29 dB. So we can check for the different attenuations, like by increasing the space or spacing between the feed lines. That is, now earlier we have given it as S as 0.3, and we can also check for 0.2, and the thickness of the material which we have defined in the conductor definitions as tan D is equal to 0.025, and now we can change it to 0.001, and we can analyze the results. Thank you. The structure is designed to resonate at 2.5 GHz frequency that we can observe by S21 transmission line parameters. Input signal is applied to port 1 and transmission through the structure is observed at port 2. So port 2 is going to act as the output port. As from the resonator theory, maximum power is delivered to the output port 2 at resonant frequency, and rest of the frequencies the transmission reduces. As it can be observed from the simulation result, maximum transfer power occurred at resonant frequency 2.4 gigahertz, and ideally we need to have the S21 parameter as 1 for the maximum power transmission, and when it is measured in dB it should be at 0 dB. But here we are seeing that the maximum power transmission is at -28.9 dB. There is an insertion loss. Due to losses in the structure, entire power is not delivered to the output at resonant frequencies. So we need to now increase the resonant frequency as well as reduce the losses by using the low loss substrate. So the low loss substrate can be used by varying the value of the tan D. So lower the value of the tan D, the losses can be reduced. So now I will show you how to reduce the losses. In order to reduce the losses, go to the enclosures, double click on enclosures, go to the material definitions, and in material definitions you now need to vary the tan D parameter, which was earlier set to 0.025. Now let us set it to 0.001. Now after doing it, click on OK button and save your project. So once the thing is saved, go to the simulate and analyze the graph. So you can see now, earlier the power transmission was at -28.0 dB, and now it is at -17.27 dB. So the transmission loss has been reduced now, and we are increasing the power transmission throughout the microstrip line. Still there is a loss which is due to the coupling space between the you can see the coupling space between the structure and the feed line. So this space, if we reduce the spacing also, then we can reduce the losses. So how we can reduce the spacing? So let us go for the structures, EM structure 1, and we need to change the axial parameters of the structure. Like we can give the axis of structure as 0.1, so which I have done now. And similarly for the second structure also we need to give the spacing as 0.1. Again go to simulate option. So before that, choose the resonator graph, go to simulate option and try to analyze the graph. You can see that now the power which we were seeing at the resonance frequency has been come till minus 9 dB or minus 10 dB at 2.4 gigahertz resonant frequency. So we can go on changing the parameters of tan D as well as the spacing between the feed line and the strip line, and then we can reduce the losses which are going to be incorporated in the structure. Thank you.